being here. So many of you have been here just about every class on a regular basis. And I don't think I let you know how much I appreciate your concern and your attendance. I'm going to, now that we're recording, start sharing my screen. In terms of sharing my screen, couple of things. The chapter 13 test is to be done by this Saturday. I do believe it should be available for you from today on. The chapter, and there's a separate drop box. Please open the test. If you want to, you can type your answers into the test, but it's probably easier if you just show your work on separate paper. You know, be consistent. When you show your work, please make sure that the pictures that you take are legible. I think one of the last assignments, somebody's pictures were awfully blurry and I had a really hard time reading them. Chapter 14, we're starting today. That test will be due by Monday, May 3rd. The final exam will be due by Wednesday, May 5th. The final, I'm going to make a slight difference from what was in the syllabus. The final is going to be optional. If you take the final, I will drop the lowest test grade.
What happened if the lowest grade is the final exam?
That'll be the grade that's dropped.
Okay.
Okay. If you do not take the final, I will not drop a grade, test grade. I will drop the lowest activity grade. I will drop the lowest homework grade. I can't really drop anything from the attendance grade, but if you take the final, the lowest test grade will be dropped. If you don't take the final, I am not dropping a test grade. So if you're happy with your average, you don't really have to take the final exam. In terms of chapter 14, right now, all of that work is due on the 3rd. And again, I think we had said last class, but let me spell it out here. There are going to be no chapter 14 activities because one, we're running out of time. I know that this time of the semester is crunch time for us as faculty members. We do a lot of grading and everything. I'm positive it's crunch time for you guys as students. And also most of those activities have you working together with somebody, playing a spinner game, something like that. And because we're doing this from a distance, it's tough to get together with one of your classmates and play a game. So don't worry about those activities. Before we get started with chapter 14, I do have to apologize. Somebody let me know last night that I had not yet created the drop boxes for the chapter 13 activities and homework. I did when I got home from my night class last night. I have to apologize. I waited until I got home. It was a little bit later last night that I did that because I could not remember what the total point value was for either of those. And I need that to create the drop box. But does anybody have any last minute questions on anything from chapter 13?
No.
No. All right. If not, let's start looking at chapter 14.
Actually, I had a question
Sure.
on homework.
Yeah.
I'm sorry, give me a minute. I gotta open up the page in my notebook. Page. I think I literally just confused myself. Page 710, question 8.
710, question 8. Okay.
Yeah.
I actually was looking at this with somebody else during office hours. I didn't cut and paste the words into the notebook though. Are you all right if we just read it from the book? Do you guys need me to cut and paste the question in, or does everybody have their book with them?
Fine.
So it
Fine.
says, to determine the average life of light bulbs it manufactures, a company chooses a sample of the bulbs produced on a given day by selecting every 100th bulb and testing it for failure. What's the population? What's the greater group that they're looking at? What are they taking a sample from?
The light bulbs.
The light bulbs. So the population is the light bulbs that they produce. Is this a good way to select a sample? You think it's a good way to get a sample of everything they produce during the day to test every 100th one?
No,
No, why not?
because there could be more faulty there.
But if we're going to just take a sample, we can't really test every one of them, right?
It should be more like just to take one out of a box randomly or take a few out of a box.
Okay. All right. Well, you know what? Because this asks, what do you think? As long as your explanation is reasonable, I would accept it. That's a reasonable explanation. I think if you looked at what the authors of the textbook say, most people kind of feel that picking, starting at a random place and picking every 100th or 50th or 1000th or whatever is pretty random. But again, it's an opinion piece, so that's fine. Is that sample random? And again, this is one of the ones where it's an opinion. Why? Because some people think that that idea of as long as you don't randomly pick where you start, every 100th one is a random way. Some people think it's too methodical and it's not random. So again, with those answers, it can go either way. What I'm looking for is a reasonable explanation, depending why you think that. Does that make sense?
Yes, thank you.
Okay. Any others? If not, let's start looking at chapter 14. This is the last chapter in the textbook. Because you folks took 108 and 109, you've covered all 14 chapters. How cool is that? This last chapter deals with the idea of probability. And we're going to look at probability as a measure of the likelihood of something occurring. Before we look at probability, there's a definite vocabulary that is used. And the first thing that we're going to talk about is an experiment. Can I go on the assumption that everybody in class has done an experiment at some time, maybe in a science class or something like that? When you perform an experiment, it's because you want to see what happens, because you're not certain of what will happen. So we're going to look at an experiment as something with uncertain results. In a science class, an experiment is sometimes big and involved. In a math class, when we're talking about probability, our experiments aren't going to be quite as involved. Some examples of experiments might be if I toss a coin. When I toss a coin, do I know for certain what I'm going to get? Well, take that back. Tossing a fair coin. You might have a weighted coin where it will always show up the same thing. But when you toss a coin, you usually don't know. That's why they start sporting events that way, right? Another example might be if I roll a die. And there, that word die, is everybody familiar with that. You might have heard of playing with dice. Dice is plural, die is singular. I look at the relationship between dice and die like the relationship between mice and a mouse. A die is one of a pair of dice. Another a common example of something that's looked at as an experiment in probability is if you pick a card from a deck. And you've all seen it when somebody fans out a deck of cards and says, pick a card, any card. And as long as it's a regular deck of cards, you really don't know what's going to get picked. And so that would fit the definition of an experiment. An outcome is the result of an experiment. And so we don't really have enough space here to look at the outcomes for each of them, but we can talk about them. With a coin, what are the possible outcomes?
Heads or tails?
Beautiful. When you roll a die, what are the possible outcomes?
1 through 6.
1 through 6. When you pick a card, let's see, it's 2 through 10, Jack, Queen, King, Ace, in clubs, hearts, spades, diamonds. Are you folks familiar with decks of cards? Does everybody know what a deck of cards looks like, what cards are in there? If anybody's not familiar, let me know and I'll upload a picture of a deck of cards into the folder for the notes for this chapter. Does anybody need that? So next definition then is the sample space. And the sample space is the set. And again, in Math 108, we spent a little bit of time looking at the ideas of sets. A sample space is the set. Oh dear. Of all the possible outcomes. For an experiment. And so if I look at that coin, my sample space would be the set containing heads or tails. Are you folks all right if I abbreviate H for heads and T for tails? If I look at my die, the sample space would be the numbers 1 through 6. And I have to apologize, both of my styluses are acting cranky today. And periodically they just stop working on me. So I'm going to have to pull the battery out and put it back in. I might have to end up replacing these batteries before the end of the day. So for a die, the sample space is the numbers 1, 2, 3, 4, 5. 5 and 6. Does everybody remember? With a set, you want to use braces and you want to put a comma in between those elements. The other term that we use is an event. And an event is going to be defined as a subset of the sample space. And so if I look at my coin, tossing a coin, an event could be getting a head. Tossing my coin, an event could be getting a tail. There's subsets in my sample space. If I roll the die, an event could be rolling the number 1. Or an event could be a larger subset. It could be getting an even number or getting an odd number. So the events can be any subset of that sample space. We're going to look at two different types of probability. The first one, the authors of the textbook call experimental probability. I've also seen it called empirical probability. And it's based on the results of an experiment. So depending on how many times you do the experiment, that probability could change. So it says if an experiment is repeated n times, so that's the number of times that I'm doing my experiment, and a certain outcome occurs r times, the experimental probability, notation wise, experimental probability is going to be a p with a subscript e of that event. So over here, uppercase E is the event, would be equal to the number of times the event occurs over the number of times the experiment is performed. So that's the number of times the event occurs over the number of times the experiment is performed. And I have to apologize. In an ideal world, I would have asked everybody to make sure they had a coin with them today. Do any of you have access to a coin?
No. Yes.
No. Yes. All right. If you have a coin, I'm going to ask those of you who have a coin to toss their coin. So I've got a coin here. I'm going to toss it. And what do we want our event to be? Do we want to get a head or a tail? What do you guys think?
Head.
Head? Okay, so then let's go through and let's look for the probability of getting a head. Oh dear. This is not letting me go back and sharing my screen. There we go. So let's find the probability of getting a head. And so how are we going to count this? I'm going to stop sharing my screen again. And first of all, do you guys know how to raise your hand in Zoom? How many of you have a coin? Victoria, Naomi, me, Stephanie, you have a coin? So we've got 4 people with coins. Now, put your hands down. Of those of you who tossed your coin, how many of you got a head? So based on that experiment, we had four coins and we got 1 head. Let's say those of you with coins, toss them again. I'm going to toss mine. This time, I'm also getting a tail. The rest of you, could you let me know if you got a head?
I got a head.
Naomi, did anybody else get a head?
No.
No? So if we each did it a second time, we've got a total of 8 tosses and we had 2 heads. And if we were on campus, I would have given everybody a penny. That would be my contribution to your wealth. And I would have asked everybody to toss. And as a group, we toss the coins several times, and each time our total number of tosses would increase, and hopefully our number of heads would increase. But you see how here, this is just based on the result of our experiment. And so there's something that's called the law of large numbers that says the more often you do an experiment, the more times you repeat it, the experimental probability will approach a fixed number. I'm thinking in terms of experimental probability. One thing that I've heard recently in the news a lot is, have you guys heard about the Johnson & Johnson vaccine? And they said that it's caused a rare form of blood clot. And when they talk about that, they say that 6 people got blood clots, but then they estimate that 6 million people have taken the vaccine. And so in that example, if I look at the probability experimental of a blood clot, with the Johnson & Johnson vaccine, there were 6 clots out of 6 million people who took it. And so that would be, again, an example of an experimental probability. And the more people that take it, the closer that number will get to the actual probability of getting that. So this idea of experimental probability, all right.
How did you get 8 for the second round of tossing the coin?
Because the first time when we did it, we had 1 head and 3 tails. The second time when we did it, we also had 1 head and 3 tails. So altogether, we've done it 8 times. I'm combining the results.
Okay, so you double the bottom basically?
No, I looked at, I didn't necessarily double the bottom, but rather I said, okay, the results of the experiment, 1 had 3 tails, and then again, 1 had 3 tails. So altogether, I've done my experiment 8 times.
Okay.
Okay,
Okay.
thank you for asking.
Mm-hmm.
So next question, we can sometimes get an experimental probability from a data set. And so I could look at students and their test results as being my experiment. And so here, this was a test that I had given. I can't even remember what class I had pulled that data from. It was a while ago. From that class, what's the probability that a student scored in the 90s? Well, the number of people who got in the 90s if we were to count up, how many people got a grade in the 90s? Can you guys count for me?
Seven.
7. And the number of experiments would be the number of students. And so how many students do I have? Anybody else getting 36?
Yes.
And so the experiment was performed 36 times and the event occurred 7 times. So the experimental probability of getting a score in the 90s would be 7 out of 36. With these questions, I'm perfectly fine if you leave your answer as a fraction. Some people have a tendency to divide them into decimals all the time, change them into percents. It's not necessary. I'm fine if you leave that answer as a fraction. And so that's experimental probability. It's based on the results of an experiment. Everybody okay with that one? The other type of probability is theoretical probability. And so here, if E is the event, P of E is the theoretical probability. That E occurs. And now, when I look at the N of E, remember we said was an event, was a subset of the sample space. And can anybody remember from back in Math 108, when that little n is in front of the name of a set, we're talking about the cardinality or the number of elements in the set. So it's the number of outcomes in the event. And N of S would be the number of outcomes in the sample space. And so this formula says that the probability of an event is equal to the number of ways the event can occur over the number of outcomes in the sample space. Number of ways the event can occur over the number of outcomes in the sample space. And so if I look at my coin, what's the probability theoretical of getting ahead? Well, there's one head out of the two possible outcomes, so it's a half. Everybody all right with that? So next, let's look at here, because it's just a P, these are theoretical probabilities. And so if I'm looking for a die, remember we had said that the sample space for a die was the numbers 1 through 6. And so what's the probability of rolling the number 3? How many 3s are there?
One,
Out of how many things are in the sample space?
6,
Instead, if I ask, what's the probability of rolling an even? How many even numbers are there
3,
out of the total 6?
6,
So that probability is 3 out of 6, which we could reduce to a half. What's the probability of rolling a 7? How many 7s are there?
1. Oh, 0.
0. There's no 7s. So 0 out of 6, which is 0. And do you notice the reason that that probability is 0 is because it can't happen. It's not there. And so we're going to generalize and say that if an event is impossible, its probability is 0. If something can't occur, it's going to have a probability of 0. Next one, on this die, what's the probability of getting a number less than 10? Well, in my sample space, how many of those numbers are less than 10?
All of them.
All of them. So there would be 6 out of the 6, which would be 1. And the number 1 is a percent, 100%. And so if something, it's 100%, it's got to happen. If something must occur, if an event is certain to occur, its probability is 1. Does that make sense? Something must occur, it occurs 100% of the time, its probability is 1. And so then, if I put those pieces together, I'm going to get a little philosophical on you folks. Is everybody all right that I kind of say that everything in life falls somewhere in between being impossible or definite? And so putting those pieces together, we'll say that the probability of any event will always be a number between 0 and 1. Everything falls somewhere in between being totally impossible and certain to occur. When you do a probability problem, the smallest value your probability can be is 0. If you do a probability problem, long drawn out multi-step problem, and you get a negative answer, there's something wrong there. Probability cannot be negative. In the same way, the largest answer you can get for probability is 1. If you go through and you do a probability question and you get as your answer an improper fraction, something bigger than 1, there's a problem. Probability is never smaller than 0. Probability is never larger than 1. So over here, I've written the outcome for 2 dice. And I have to apologize, I did not leave enough space to draw this outcome. So I'm going to flip over to, this is referred to, you know what? I'm just going to add a blank page. So let's write see next page. And so when I look at the outcome for 2 dice, to help me look at this, I draw like a matrix, a chart, so to speak. And the first die can be 1, 2, 3, 4, 5, 6. And the second die can be 1, 2, 3, 4, 5, 6. And so I could get 2 1s. I could get a 2 and a 1, a 3 and a 1, a 4 and a 1, a 5 and a 1, a 6 and a 1. I could get a 1 and a 2, a 2 and a 2, a 3 and a 2, a 4 and a 2, a 5 and a 2, a 6 and a 2. I could get a 1 and a 3, a 2 and a 3, a 3 and a 3. And do you guys get the follow the pattern here? Do I have to keep on stating them, or can you fill them in on your own? And so that's my sample space. Listing all of my possible outcomes. How many things are in the sample space? How many possible, that's an S, by the way. How many possible outcomes are there? Well, there would be 6 times 6 or 36 pairs of outcomes. And so what's the probability that I get where it says 2? It should be the probability of getting a sum of 2. How many of those outcomes add up to the number 2? I think over here, the 1 and 1 is the only way of getting it. So that probability be 1 out of 36. The next asks, what's the probability of getting 1? How many of those outcomes add up to the number 1? If I have 2 die, is it possible to get a total of 1?
No.
No. So that probability is 0 because that's impossible. What's the probability that I get by 6? I mean a sum of 6. So I'm looking for number of pairs that would add to 6. So let's see, 1 and a 5 add to 6. 2 and 4 add to 6. 3 and 3 add to 6. 4 and 2 add to 6. 5 and 1 add to 6. And you notice that that sum is along the diagonal here. But I'm counting 5 that total to 6 out of the 36. And then what if I ask, what's the probability that I get a total of 12 when I roll those 2 dice? How many of those number pairs add up to 12? I'm thinking 6 and 6 is the only one. So that would be 1 out of 36. Everybody all right so far?
Yes.
Then the author, I'm trying to cover the material in the order that the authors of the textbook do, which is somewhat jumbled to me. They kind of play hopscotch all over the place, but trying to follow the textbook. The next thing that the authors talk about is mutually exclusive events. Mutually exclusive events are disjoint subsets. They have no events in common. So they have nothing in common. There's no overlap. You might remember from your study of sets in Math 108 that the idea of disjoint sets is that their intersection is empty. And so we were going to next look at this idea of mutually exclusive events with experimental probability. And with experimental probability, I would have given everybody in the room a pair of dice, and I would have asked everybody to roll them 10 times. And so for the number of folks in class today, we would have had, oh, I have to go back and look at attendance, but if we've got 10 people with us, we would have had 100 experiments, right? We would have had 100 rolls. And we would have been able to count the number of times people got a total of 1, 2, 3, 4, 5, 6, through, I'm sorry, 2 through 12. I have to apologize. I'm not clever enough to figure out how to do that through Zoom without it taking an hour to get everybody's results. So I'm going to replace this experimental with theoretical probability. I'm sorry, it's more fun if we rolled the dice and used our outcomes, but it's a little bit difficult to do. And so what I'm going to do is I'm going to take this table that we have, this table that we have for possible outcomes, and I'm going to copy that and whoops, something went wrong there. Paste that here, if it lets me. Oh Lord, that's way too big. Let's see if we can shrink this down a little. Well, shrink this down a little bit. No, we can't. So we're going to reverse. Oh, it's not even letting me move it anymore. Would it have been easier to just rewrite the numbers? Well, we've got them sort of off to the side there. Okay, we can sort of move it in. So using this, what's the theoretical probability? I'm going to cross out the little e. What's the probability of getting a total of 4? Which ones add up to 4? 1, 3, 2, 2, 3, 1. And so that probability is 3 out of the 36. The probability of getting a 6, I think we found already on the other page. We said that the probability of getting a 6 was 5 out of 36. That would be these 5 here. And so what would be the probability of getting a 4 or a 6? Any ideas? How many of those outcomes are either 4 or 6? Is anybody getting between the two of them 8 out of 36? Then the next one, if we're looking for the probability of getting an even sum, well, let's see, even numbers. Those would be 2, 4, 6. Then over here, it would be 4, 6, 8. And over here, it would be 4, 6, 5. And this row would be the sum of the two evens. And this one, it would be the sum of the two odds. And this one, it would be the sum of the two evens. And so I'm looking at it, and does it make sense to say that that's half of my outcomes, or 18 out of 36? Then we're looking for the probability, I'm going to just cross out the little e, that I got a number bigger than 9. Well, let's see, bigger than 9, I'm going to use, oh dear, What color haven't we used yet? I guess I'll use I'll use the gray. Bigger than 9. Well, that could be 10, 11, or 12. And so bigger than 9 is 1, 2, 3, 4, 5, 6 out of 36. Is everybody, you guys are being so quiet today. Is everybody all right with where I'm getting all of these fractions from?
Yes.
So now over here, what's the probability of getting an even or a number greater than 9? Up here, the 4 or the 6, I could just add them. But here, the 4 and the 6 were mutually exclusive. They don't have anything in common. But here, if I compare the ones that I circled that are greater than 9 and the ones that I highlighted that are even, do you guys see that these are not mutually exclusive? They have some overlap. Some of the highlighted ones were circled. Some of the circled ones were highlighted. They have something in common. And so if things are not mutually exclusive, we're going to say that the probability of A or B is equal to the probability of the first one. So that would be here when we're looking at the probability of even or greater than 9, that would equal the probability of the even plus the probability of the second one greater than 9. And then we want to subtract the probability that they both occurred at the same time. Kind of the idea that we don't want anything to count twice. So the probability of even was 18 out of 36, plus the probability of being greater than 9 is 6 out of 36. But then we have to subtract the overlap, which sums were being counted twice. And here, do you see between the circled ones and the highlighted ones, there were 4 sums bigger than 9 that were also even. So we'd have to subtract that 4 out of 36. And so 18 and 6 is 24 minus 4 is 20 out of 36. So if they're mutually exclusive, it would just be the probability of the first plus the probability of the second. And this piece there wouldn't be anything if they're mutually exclusive. There's nothing in common. But if they're not mutually exclusive, we have to remember to subtract the ones that got counted twice. Does this make sense? Your
Yes.
silence is yes? Okay, good. I just looked at the clock and it's that time. So if everybody's all right, I'm going to wait. No, I'm not. I'm going to go back. Oh dear. Here and share my screen one more time to go back to the top page. Please remember that to do that chapter 13 test should be available from today until Saturday. And please make sure you turn in those chapter homeworks and activities. Having said that, I'm going to stop recording